Okay, we're in section 5.3. It's the homework, and certainly we'll go through the homework. My goal here is, though, to tell you that it's not me going through the homework, it's you going over the homework. All right, you need to do homework. All right. We often talk about in education, why there's such a wide spectrum of achievement. And some people just simply say it's because, some students are better than others. And I think that that's partially true. But the other real big truth about this is the amount of time some students spend on their studies. The more time you spend on your studies, the more likely it is that your studies will pay off. All right. Now, there's a tremendous trend in education where we tend to be pumping out a lot of people with, high school diplomas and college degrees. And unfortunately, pumping them out doesn't mean they're educated. All right. So we're not here to pump you through the course. We're here to try to encourage you. That the encouragement is that you try to do things. And as you do things, you're probably going to get better at those things. All right. Now, I'm not going to say that if everyone put the same amount of time in, that all the outcomes would be rosy. They wouldn't. I mean, some people are just simply naturally talented at doing things. Other people are not. I would say the majority of people, though, the reason they don't do well in school has very little to do with talent and much more to do with time spent on task. All right. So what I'm going to do over here is I'm going to go through the homework, and certainly, I can't say I enjoy doing your homework, but I'll be honest with you, I don't dread it. Like I think of myself, if I had to kill a few hours, it's better to do this and play a video game, for example. A video game might be more entertaining to you, but my mind is somewhat engaged when I do these problems. I have to think, I got to do certain things. I'm not learning anything new, but I am doing something. And by the way, I hope you're not learning anything new by doing these problems either, that this is run-of-the-mill problems. Are you going to make mistakes? Of course you're going to make mistakes. We'll go through it. There's not many problems, though. For me, if I had to look at this assignment, I would say, gee, this is not too bad. I want to give you just a little anecdote over here. I've been around school my entire life. I do know one thing, that typically, particularly my education as well, that, like I was actually in mathematics classes where there really was no homework. I mean, someone says, oh, gee, that must have been great. No homework. It must have been so easy to get through that course. Just the opposite. So what students end up doing in the courses with no homework, they'd have to get a book and do every single problem in the book. Every single problem. And some of these books, by the way, I mean, literally could take you hundreds of hours to get through one section. The problems are so difficult. I'm doing a little research project now on an algebra book from I think it's 1905. And the problems in the book are substantially more difficult than I'd ever seen in an algebra textbook before. So things really, I want to point out, as far as the homework space, things have gotten a lot simpler. I mean, we tend to get problems that are simple to do. We don't give you many to do. And then exams come up. Exams tend to be rehashes of what the homework was about. So I would take this to heart, and sort of say, so if you really want to be an aggressive learner, you're going to have to do more than we're asking of you. But right now, our goal is to get everyone up to this speed. What's the speed we're talking about? You doing problem sets. All right. So I'm going to switch screens now. And I'm going to go through one problem at a time. And again, there's not many problems. Should get through it quickly, including if I'm daydreaming. All right. I daydream sometimes when I'm doing the problems. But let's take a look one problem at a time. And I'll certainly, when I'm doing these things over here, I'll tell you what I do first. It says calculate the volume. Yeah, I'm reading first. Calculate the volume of the solid obtained by revolving the region under the curve. Gee, that's 1 over x. That's pretty simple to deal with. About the x-axis on the interval 1 to 4. Well, I'm going to draw my little picture on the side. And I know they said 1 to 4, right? So I'm going to put that over here, 1 to 4. That's x equals 1. And this is about 4 over here. X equals 4. And there's a curve, and that curve is, 1 over x, which is, looks sort of like this over here. I'm going to put these points down for you. And this point over here is going to be 1, 1. And this point over here is going to be 4, 1/4. And let me talk about the region. I'm going to shade that region in for you. And this is the region they're talking about over here. And again, no, I'm not saying it's the best picture in the world, but it's enough for me to say, I think I know what they want me to do. Here's the problem though. If it takes you a long time, you may make up what they want you to do. And that's bad. Like you can't remember what you read. Well, I'm going to read it again to you. It says, calculate the volume of saw obtained by revolving this region. I just drew the region under the graph, blah, 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 about the x-axis. So I'm going to draw a little like rotation thing over here. And what I'm going to do is I'm going to draw a representative rectangle. And if I rotate that rectangle about the x-axis a full 360 degrees, what I'd get is a disk. Looks sort of like this over here. All right, where this would be dx, this would be r, and the volume of that would be pi r squared dx. Now I'm going to put my integral down. Right, because I'm going to add all those disks together. So if we can do that, and again, we have an ASCII to check. So it's going to be from, let's see, from 1 to 4 pi something squared, that's the r squared dx. What's the r? It's actually y. And what's y? Y is equal to x to the minus 1. Put this over here. Now what do I have to do? I have to do the integration. And what do you get there? Well, let's see if we can do that. That would be pi, that's a constant, 1 to 4, x to the minus 2 dx. Let's keep moving forward. Whoops. This would be pi. Let's see, x to the, I add 1, right? So minus 1 over minus 1, and that's 1 to 4. Oh, this is minus pi over x from 1 to 4. This would be minus pi over 4 minus a minus, which is plus pi over 1. I'm going to add that together. Common denominator is 4. So it'd be minus 1 plus 4, which is 3 pi. And these are going to be cubic units. Hey, I wonder if I got that right. Bingo, got it right. Let's go to the next one. Let's see what we got over here. Find the solid obtained by the region graph, blah, blah, blah. Gee, look, same problem. But this one is between 0 and pi over 2. So if I were looking at f of x at 0, it would be 0. And at pi over 2, what would it be at pi? Also 0. Pretty simple. Now, what do I know about the sine function and cosine function between 0 and pi over 2? I know it's positive. I should say non-negative. And what else do I know about it? If it's non-negative, the root of it is certainly defined, and the root of that's going to be a positive number. So I'll do maybe something like this over here. Let me shade the region in. No, it doesn't be accurate. I'm not saying it is accurate, but I do want to shade that region in. Again, if I can't remember what I've read, I'll just keep rereading it until I can figure out what they want. So find the volume of the solid obtained by rotating this region under the graph of this thing over here about the x-axis. Well, I know this is being rotated. Oops. Like this, about the x-axis. So I'm going to put my representative rectangle in. And if I rotate that, I'd get a disk. Look like this over here. All right. This is the r, and that's the dx over here. This is the r. Oh boy, this looks like it might be a tough one. Let me point out to you, they're never going to be tough. They're always going to be doable. We do not give you things you can't do. We want to develop full confidence in that. We don't want to give you anything you can't do. Could you write problems you can't do? Of course. If you want to look at a set of problems you can't do, I'd be more than happy to give it to you. I'd even give you like algebra problems you can't do. I mean, some problems are really difficult and you can't do them. All right. I'm not saying not everyone. I'm saying most people can't do them. They're just too difficult. Let me write this down. 0 to pi over 2 pi r squared dx. What's the r? Well, it's actually the y, or the function. And what's the function? It's this thing. Well, I'm ready to go. I sure want to look at their work. So let's put this over here. What do you get? Pi 0 to pi over 2. If I square that, that's pretty simple. What do you get? Sine x times cosine x dx. I want to do this. I'm thinking back to what I did in math 121. I think we had u substitution. You remember that? Let me see if I can do that. Let me see if I can do u substitution. So u is equal to sine x, and du would be cosine x dx. Gee, that worked like a charm, didn't it? Pi. Well, let's see. I know u now. I'm going to go to the land of u's. And what's the sine of 0 is 0. And what's the sine of pi over 2? It's 1. And then what do I get? Well, sine x is u, and cosine x dx is du. Well, I get something pretty simple up here. What do I get? Pi u squared over 2, 0 to 1, which turns out to be a very simple integration problem, pi over 2. And these are cubic units. They didn't give me any measuring. Now, I'm going to go back to the key, and I just want to make sure I see pi over 2. Now, by the way, someone says, oh, they did it differently. You're right. They did it differently. What they did, they used double angle formulas. But here's the deal. I'm not saying that double angle formula is going to make it any easier for you. In fact, I think one day I might use double angles. Other days I might use u substitution. Who knows? Maybe I'll do something else on the third day, right? Have options, though. Options are nice. Would the answer ever change? No, the answer is never going to change. All right, let's go to number 3. And again, I'm hoping these are relatively simple. Last question, a pretty simple problem set. And certainly what I'm doing is thing over here. This is number 3. Oh boy, I got to graph this out, don't I? And what do I got? I got x squared, looks like this over here. Not the best looking picture, but you get the idea. And then I got 2x plus 3. That's a line, y-intercept of 3, maybe something like this over here. And there's points of intersection. And I know there's a region now. I really haven't read it completely. I wonder what they're going to, and that's the problem with if you don't read, you think you know what they said. Maybe they're not saying anything above, and I'm just assuming they're talking about this over here. Let me just shade this region because I think I see a region now. All right, I got to find those points of intersection now. Let me see if I can do that. So what do you get over here? I'm going to set x squared. Oops, I did something bad there. X squared is equal to 2x plus 3. Again, I want to emphasize students not seeing this. I'm looking at these functions here. I just graphed the x squared problem and I graphed the line 2x plus 3. Again, I'm not saying it's terribly accurate, but it's sort of that picture. I'm not saying it's perfect, right? So I wonder if I could solve that. And it'd be awful if I could, wouldn't it? Whoops, did that again. So x squared minus 2x minus 3 equals 0. X and x. 3 and 1 minus plus. Yeah, it looks pretty easy. Minus 1. I'll do the y later. And this looks like 3 over here now. Wow, this is working out really nicely. So if it's minus 1, I want to point out, I'm substituting here because it's easy for me. That would just give me the number. Let's see, 2 times minus 1 minus 2 plus 3 is 1. Looks reasonable. And if I did the 3, what would I get? 2 times 3 is 6. 6 plus 3 is 9. Okay, so I got the points. I got a picture. Let me read it to you. Find the volume of the solid obtained by rotating the region enclosed by the curves about the x-axis. I'm still doing this. I'm still rotating. So you know what I'm going to do? I'm going to do my representative rectangle. And that looks like this. But I've got troubles. I'll tell you what my troubles are. I've got this big guy here. But after I do the big guy, I got to remove something from it. I got to remove the little guy from it. Let me point out what the little guy is over here. It's the little guy. So let me do the big guy first. He's the blue guy. You just blue guy first. I'm going to write its integral down. All right. So what's the integral going to be? Well, the differential is dx. I'm starting at minus 1 and I'm going to 3. pi r squared dx. And then I'm going to remove the little guy, a hole, so to speak. Let me write that down for you. We haven't gotten this r down yet, though. Minus 1 to 3 pi r squared dx. Now, again, I want to point out the big guy, the top is this line over here. And I'm not memorizing the line. What's the line? 2x plus 3. That's what the y value is. That's what I'm looking at. And how about the little guy, the guy that we're drilling away? That's just x squared, isn't it? Well, you know what I'm going to do? I notice I can take these two integrals and write one down. It might be easier for me to do. I don't know. Maybe not. So what do you get? Pi minus 1 to 3 4x squared plus 12x plus 9 minus, I'm taking these two integrals, pulling them together, by the way, x4. Now, do I make mistakes? Yep. Will I know I made a mistake when I look at my key? Maybe. I don't know. Let's find out. Now, what do you get over here? Pi 4x cubed over 3 plus 12x squared over 2, which would be 6x squared, plus 9x minus x5 over 5. Limits integration, minus 1 to 3. Now, someone's going to say, are you going to do that arithmetic? You bet I am. Let's see, let's put the 3 in first. What would you get? Oh boy, one of the 3's would cancel. You get 4 times 9, 36. Plus 6 times 9, 54. Plus 9 times 3 is 27. Minus 3 to the 5th power. Let's see, 243. You know what? I'm not sure. So let me check that out. 3 times 3 is 9, 27, 81. 81 times 3 is 243. I feel good about that now. So the next one, minus pi. I'm going to put a minus 1 there, so it's minus 4/3. Again, if you can't do arithmetic, walk away. I mean that. It's a fight you can't win. Plus 6, minus 9, and that would be plus 1/5. And again, I can't say I'm not good at arithmetic either. I mean, make mistakes all the time. And I don't like making mistakes, but I make them. I'm going to start adding things together that I think are easy to add together. So 36 and 54, that's 90. 117. Let's see, I think I can handle it. And let's see, 6 minus 9 is minus 3. And minus 4/3 and 1/5, that's a common number of 15, right? So let's see, minus 20, minus 17. Let me just check it again. Let's see, 3 and minus 20. Yeah, minus 7. Keep going. Let's see, pi. I'm going to do these two guys now. So 117 minus a minus 3 is 120. Boy, this is going to be a tough one, isn't it? Minus 243 over 5 plus 17 fifteenths. I don't know if I can handle it. Let's see if we can do it. Pi 120. I'm going to say a common error of 15, right? It's going to be minus. I got to do some arithmetic on the side and give me a moment. So 3 times 243, 600, 120, and 9. So that would be 729. I could take 17 from that. What would that give me? That would give me 7, 1, 2. Got to do more work, huh? Let's take a look. 15. Well, I got to do 15 times 120 now. Let's see, 600, that's 1800, and 1800 minus 712. That doesn't look too bad. 1088, right? So I'm going to say, maybe I made a mistake. All right. Richard tried the worst thing about that problem. Bingo. All right, we did all right. This is good news. Do I make mistakes? Yep. Do you make mistakes? Yep. Let me point out the biggest mistake most people make in their lives has to do with their educations. They don't take them seriously. And you really do need to take your education seriously. It takes time and effort. If you're looking to master a skill, it takes time. Some people say, can I take as much time as I like? Well, yeah, but you realize life is finite. So you want to try to speed the process up a bit and become more productive. Thank you for paying attention.